Okie dokie. So let's consider the context-free grammar for English, a baby part of English. So a context-free grammar for English. Okay, so my start variable is s. Okay, and if I want, I'll label the rules. S can become either a phrase or S is replaced by a phrase verb. Now, okay, everything here is variables, so there are no terminals. So let me list my variables. So far I have the variables S and phrase and verb. So this is an example where I'm choosing unusual names for my variables, and that's because it's going to make things a lot clearer with respect to English, which we're familiar with. So in English we're familiar with phrases and verbs and so on and so forth. So I'm going to write my context-free grammar using the terminology that we're familiar with. Okay. Now, what can you do with a variable phrase? So phrase can transition to, so this is a production rule, transitions to an article and a noun. So you can think of this as something like an or an a dog. Okay, and so now we've introduced two new variables. We've got articles and nouns. Okay, these are variables. Okay. And what can a noun transition to? Okay, so a noun can transition to either cat with a space or dog with a space. So these are now characters. So my strings are, going to involve the characters in English, the standard alphabet. Okay, so now I have some terminals. So one terminal is cat, and the other terminal is dog. So those are not variables. Okay. What about my articles? My articles can transition to either a with a space or the with a space. Okay. So now I have two more terminals. I have a with a space and the with a space. So you see how this is starting to look like English, except what is this? It's all nonsense. It looks like gibberish. Well, what I'm doing is I'm defining a context-free grammar for baby English. Okay. Okay, so what else do I have as variables? I've got phrase, noun, article. What about the verb? Okay, so what about the verb? Verb can transition to either walks, dot means period, okay, runs, dot, okay, walks, dot, space, s. Now s is a variable, and runs, dot, space, s. Okay. So let's see some things that we can derive with this grammar. What kind of strings can we get? Okay. Now, well, we start the usual way. Start with, s. Okay, it produces phrase verb. So I'll just write that as PV for phrase verb. Okay, and phrase can be replaced with article noun. Okay, so this can go to article, noun. Okay, I'm just using shortened so that I don't have to write, but technically I should write phrase, verb, article, noun. So that replaced phrase. Okay, and then I still have to keep my verb. Okay, so you take one of the variables and replace it. Okay, now, I can pick one of these three. Okay, I'll pick the article, and so I can replace the article with a space. Okay, so a space, and then I have my noun, my verb. Okay, and we can continue going. So my noun can be replaced by, for example, cat. I can pick either cat or dog. So a space, I replace my noun with cat space, and then I still have my verb. Okay, and I have only one more variable. So I can replace it with walks. Okay, dot, because I could go here. Okay, so let's put the rule numbers. So this guy is rule number 1. This guy replaced the phrase. So this is rule number 2. Okay, this guy replaced the article. So that's rule number 4. Okay, this guy replaced the noun, so that's rule number 3. Okay, and finally we're going to replace the verb. Okay, so rule number 5. We're going to replace the verb with runs. So we get a cat runs, dot. And so you see how this beautiful context-free grammar can be the beginnings of a formal methodology for generating grammatically correct strings. And in fact, you can now take any string and see, can it be generated? In which case, it's a grammatically correct string in this baby English. Okay. You could imagine what would happen if instead of replacing, verb with runs, okay, instead I could have replaced, I could have gone a different path. I could have replaced the verb with runs, dots, space, S. So I would have gotten a cat runs, dot, space, S. Okay. And now what happens? So this S here and this S here, which results in this S here, now gives me the ability to generate another sentence. And so now I can generate essays. Okay. So you should be confident that, or at least get confident and do this exercise and generate, an essay like a cat runs, the dog runs, a cat walks, the cat walks. You can generate all kinds of things, but it's very simplistic. They'll all be phrases of that form. A cat runs, a cat walks, the cat runs, the cat walks, a dog runs, a dog walks, the dog runs, the dog walks. So if that's all you ever wanted to say in life and you wanted to say it grammatically correctly, bam! There is the context-free grammar for that baby English. Okay. And now you can imagine what would the context-free grammar for real English look like. Oh, well, sit down and try to write it out. And then you will have a formal prescription, for English. Okay. Now, let me mention what we mean by context-free. Okay. So you could imagine, so context-free, so we have the verb here, and we had the verb here, and you can think of this verb as being in the context of a cat. Okay. Now what makes this a context-free grammar is you can take any production rule for the verb and replace that in here, no matter what the context is. Okay. So, as an example, supposing we also had verbs barks, dot, and, meows, dot. Okay, so if we had those as verbs, now in the context-free grammar, you could then produce a cat verb, could be a cat barks. And you could produce a dog verb, could be a dog meows. And now we're getting to more sophisticated English, which is context sensitive. It says that, you cannot replace the verb no matter where it occurs with barks. You can only replace the verb with barks depending on the context. So we're studying context-free grammar, but you could imagine thinking of things like context-sensitive grammars, which, when you see a variable, what you can replace it with depends on what has gone on around it. Well, that's much more complicated. Let's at least, get to grips with context-free grammar. So you can replace this verb with any of its production rules, no matter what the context is. Context-free grammar. Okay, let's do a baby context-free grammar for programming languages. So, let me write down a baby context-free grammar for programming languages. Here it is. So you have your start variable s, so this is the first production rule, can become either a statement with a semicolon and s, or just a statement, with a semicolon. Semicolon is something that's popular in most programming languages to help, separate statements. So now, think to yourself, here basically what I'm saying is that from my start variable, I can produce a statement, and here I'm saying I can produce a statement, followed by S. What is that followed by S doing? And if you think about it, you'll realize, what it's doing is it's allowing me to sort of replace this S with another statement, okay, or another statement and S. So basically what this S here is doing is it's allowing me to concatenate any number of statements I want. Okay, so that's a very powerful tool. It just allows me to concatenate. All right, and what can we do with a statement? So a statement, so the variables are so far S and statement, STMT. Okay, and we have the terminals. So far we just have the semicolon. Now a statement can be either of the form assignment or a declarative statement. Declare. Okay? And what's an assignment? Okay, and what's a declare? Declare. So this is what we need to do now. So we've got assign as another variable and declare as another variable. Okay. So an assignment and a declare. So a declare can either be, of the form standard declaration in, let's say, something like C, int space variable. Okay, and the assignment is of the form variable equals integer. Okay, so this is, let me write it out, integer. Okay, so now we've introduced more terminals. So we've introduced the equals and we've introduced the int space. Terminals just mean they're not variables. You can end derivations there. Okay, and we've also introduced a new thing, two new variables, which are the integer variable and the variable. So what we call a variable. So we have a variable and we have the integer. Okay, so I have to tell you what you can do with variables and integers. Okay, so an integer can become either another integer, okay, followed by a digit, okay, or just a digit. So we've introduced another variable, which is called the digit. Okay, and the variable can be replaced with either x or x followed by a variable. So let's think about what this allows me to do. If I get to the point of a variable, so what are my terminals now? I've introduced some terminals, which is x. What does this allow me to do? It allows me to take a variable and call it x. Okay, or I can call it x followed by a variable. But then that variable could be replaced by x. So this variable could become x, it could become x, it could become xx variable, which could be xxx. So this is a rule that allows me to produce an arbitrary string of x's as my variables. So my variables are going to be named only with the character x, and we'll see this in action. Okay, so what else? Have I got everything? I've got digits now. What are digits? One final rule. The digit, okay, can be replaced by, can transition to either 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Okay, so I've got a whole bunch of new terminals. 0, 1, 2, 3, 4, up to 9. Okay, now let's see what we can derive in this context-free grammar. So, and you can play with this now. This is a baby context-free grammar. Well, it's a context-free grammar for baby C++ or baby programming language. Let's see what we can get. Okay, so let's start with our variable s. Okay, and it can become a statement with a semicolon followed by a s. And now I have two variables. I can pick whatever I want for those two variables. So let me pick, I'll start with s here. So this can become a statement, semicolon, a statement. So I replace this s. So I've gotten two statements next to each other. Nice. Okay. And now so the philosophy here is I can derive this statement in any way I want, and this in any way I want, independently of that. They don't need to produce the same thing. Okay? So this guy, I'm gonna make it a declare. Okay. Now, of course, when you get good at this, you start doing all these things simultaneously. But for the moment, let's stick to the formal rules. Okay, and then we still have our statement. And then this guy, I'm going to make, I'm going to now take this guy and do declare. And I'm going to make this guy an assignment. Okay, and then this declare, I'm going to make it int, variable. So this is int space variable. Wow, this is a long derivation, and we get assign. Okay, so this went to this, declare assign state. Okay, and variable, I'm going to make x. Okay, so int x. And then I have an assign. Okay, so I've brought this guy now down to int x. Okay, and now I'm going to do my assignment. So this becomes int x, an assignment. So what shall I do with an assign? It can become a variable equals an integer. So variable equals an integer. Okay, and so now I have int x. I'm going to take my variable to x. X equals an integer. Oh, I've forgotten my semicolon. That was already there. Integer. Okay, now I take my integer and make it a digit. Okay, so int x, x equals, and I can make it what, a digit. Okay. And now finally, I'm going to end the derivation by making the digit equal to 5. Int x, x equals 5. Boom! There, I've derived this pair of statements. Interesting. So, what we say is that this statement is syntactically, or it's a valid statement in this grammar. Okay. Now, I urge you to show that the following is also a valid statement. X equals 5, x int x. Okay, and I also encourage you to show that the following is a valid statement. Int xx, x equals 5. So this guy, and that guy we derived. All these are valid statements. Okay, so they can be derived in this grammar. Okay. But now if you're writing actual code, you will realize that among these three statements, the only one that makes any sense is this guy. Because you declare the variable x first, and then you set it equal to 5. Here, you're setting something equal to 5, and the program will not know what the heck you're declaring. What is this x? It'll say, undeclared variable. You're declaring x too late. And here you've declared x, and you're setting x equal to 5. You'll get an undeclared variable. Now, so that's important. So a compiler does more than just, test if it's syntactically correct. Can it be derived from the language? It also checks the meaning that everything is in the right order. So it's a much more complicated grammar than just a context-free grammar testing if it's syntactically correct. Okay. So, this has meaning. These don't work. They don't have meaning. So not only must it be syntactically correct, not only must it be valid in the grammar, but it also, must have the right meaning. Okay, so compilers are more sophisticated than just syntactic correctness, and you already knew that. Okay, and we can derive grammars for HTML, so that we can do HTML parsing. We can derive grammars for arithmetic expressions, so we can do arithmetic expression parsing, and so on and so forth. That's the power of grammars. Okay. So now, let's address the following question, which is, supposing that I gave you a language. Okay, how do you go about getting a grammar for that language? Okay. So let's erase.